Exponents are usually written as some base raised to some power. So you got the base part and you got the exponential part. What does this mean? It means this is a shortcut for writing base being repeated 8 times, being multiplied 8 times. So for example, if I had n to the 4th power, this is saying that n is being multiplied 4 times. So that is being repeated 4 times. Instead of writing n times n times n times n, that's a little bit much, right? We can just say n to the 4th power. Another example here is y to the 7th. That is the same as taking y and repeating it by itself 7 times. So multiplying by itself 7 times. Okay, so y to the 7th is way easier, right, than writing y multiplied by itself 7 times. Another example here. In this case, there is multiplication going on here, right, between 4 times x to the 5th. So this is actually the same as 4 times x multiplied 5 times. If our equation looked like this, 4x all being raised to the 5th power, then that would be 4x times 4x times 4x. That is when it would be repeated 5 times. So there's a distinction. Parentheses are very key when we are expanding out exponents, because this means that everything is being multiplied 5 times, like repeated 5 times, versus something like this down here, where only the x is being raised to the 5th power, so only the x would be repeated 5 times.
All right, so if we're given something like this, x to the 3rd power times x to the 4th power, and we want to simplify this. Let's expand both of these pieces so we can see what's happening. So this first one is saying x times x times x, and then it's being multiplied by the second one, which is x times x times x times x, right? We have x to the 3rd power here, and then x to the 4th power here. And this is happening 7 times. So we can simplify this as x to the 7th power. And what do you guys notice about 3 and 4 and then 7? Let's try another example. Okay, so if we expand that, we'll expand this. So we'll have p times p, and then this one, right? And now we have p to the 5th power. And so if we see here, 3 plus 4 equals 7, and 2 plus 3 equals 5. So when we are multiplying two things that have the same base, this is key. You have to notice that the base is the same. These are both x's, these are both p's. When you're multiplying things that have the same base, we can use the shortcut where we just add the exponents. Okay, so if we had m to the 100th power times m to the 5th power, I don't want to write that out and expand the whole thing. That's going to take a really long time. So I can just use the shortcut, and I can say that this is m to the 105th power. All right, what if we have an example where instead of being multiplied, what if they're being divided? If I were to expand this out, x to the 4th is the same as x times x times x, all over x to the 1 power is just x. We can see here that we can make some giant ones like we talked about before. So x divided by x is just 1, because anything divided by itself is just 1. So now we have technically 1 times x times x times x. 1 times anything is just that thing, right? That's our identity property, so we don't actually need to write it. And this is the same as x to the 3rd power. Notice here we got 4 on top, 1 on the bottom, and we ended up with an exponent of just 3. What if we had y to the 7th over y to the 3rd power? All right, expand this out, we got y times y. All right, that's 7 times, and then divide by y to the 3rd power, which is y multiplied by itself 3 times. Again, we can make some giant ones. Y divided by y is just 1, y divided by y is 1, and y divided by y is 1. So I'm actually just left with these 4 y's up here. So this is the same as y to the 4th. Notice again, we had originally an exponent of 7 and then an exponent of 3. And when we simplified it, we ended up with 4. Our shortcut for this is when our bases are the same and they're being divided, I can just take my top exponent and minus my bottom exponent, and that will be my simplified exponent. All right, so now we're going to talk about what if you have an exponent that's raised to another exponent. Let's look at this as a whole. We have this entire piece is being squared. So let's just rewrite that. Instead of writing squared, we'll just rewrite it as repeated multiplication. So we'll have 3k to the 5th times 3k to the 5th. And remember that when you have a number by a variable, that represents multiplication. So this is saying 3 times k to the 5 and 3 times k to the 5th, right? So we can rearrange this because since they're all being multiplied together, we can just rearrange it to be 3 times 3 at the front and then k to the 5th times k to the 5th afterwards. So now we can see that we can use some of our shortcuts over here. So first, let's simplify this 3 times 3 part. We know that 3 times 3 is 9, so we can simplify that as 9. And then using our multiplication shortcut over here, we know that when we have two bases that are the same being multiplied together, we can just add the exponents. So we will add m plus n, which is 5 plus 5. So we'll have 9 times k to the 10th. So this would be our simplified answer from this one up here. So just like there's a shortcut for multiplication and division, there's a shortcut for this one. So if we look at this exponent here, we got 10. And then if we look at this exponent here, these exponents up here, we have 2 and 5. And so the shortcut for the power rule is you multiply the exponents. If you have an exponent raised to an exponent, you're going to multiply them together. So the key thing that we have to remember when we have something raised to a power is that every single part of this parentheses has to be raised to that power, not just what the exponent itself. So this 2 is saying that the 3 is squared, and it's saying that this k to the 5th is squared. So 3 squared is 9. That's how we got this 9 down here, 3 times 3. So 3 squared is 9, and then k to the 5th squared, that's where the shortcut comes in. We have 5 times 2 is 10, so k to the 10th. All right, so if we have this example here, 4p cubed, and this whole thing is raised to the second power, we can use our shortcut over here. So we're going to take this exponent, and we have to remember that it applies to every single piece in that parentheses, not just the exponent itself right here. So 4 squared is 16. We always have to remember to apply the exponent there. And then p to what power? Well, our shortcut tells us that we can just multiply these two exponents together. So 2 times 3 is 6. So 16 p to the 6th would be the shortcut and the answer for this.
All right, what if we have an example with division where we have more x's on the bottom than we do on the top? All right, so in this case, if I were to rewrite this, this is x times x is the same as x squared, and it's the same as x to the 5th power. So if I were to use my giant ones again to simplify, this is 1, this is also 1, x over x is 1. It's still being multiplied by 1 on top. Some people forget that, like it's not like 0 on top, but it's still 1. So I'm still with the 1 over, and I have 3 x's on the bottom. Okay, if I'm looking over here, remember our shortcut is that if I have the same base, I can subtract my exponents. So if I subtract 2 minus 5, that is the same as x to the negative 3rd power. So whenever I have a negative exponent, it actually is the same as having the positive version of that exponent just on the bottom of the fraction. X to the negative 3rd is the same as 1 over x to the positive 3rd. A lot of people kind of get confused with this, but if you write it out, it's easier to see that a negative exponent means that there's that many x's just on the bottom of a fraction. All right, let's look at another example. We got x to the 5th times y divided by y squared. If I were to expand this out, again, this makes a giant 1 and just goes to 1. 1 times x to the 5th over y is the same as x to the 5th over y. If I wanted to use my shortcuts, instead of expanding it out and canceling out my giant 1, I can come back to the beginning here. X to the 5th times y. If I just have y, that's the same as y to the 1st power, because y is just be multiplied once. And my shortcut here is that I can subtract my exponents, and when I do 1 minus 2, that is the same as negative 1. So I have x to the 5th times y to the negative 1, and using my other shortcut, I know that I can, if it's raised to the negative exponent, that is the same as its reciprocal, but to the positive exponent. So I can rewrite this as x to the 5th times 1 over y to the 1st power, because my negative 1 now becomes a positive 1, or that's the same thing as what we have here, x to the 5th divided by y.
All right, so now what if I have something like this? We have x to the 4th over x to the 4th. So I could expand it out, or I could use my shortcut. I'll expand it out first. So if we have x to the 4th over x to the 4th, all right, x times x times x times x on the top and the bottom, and then we can make ones, right? X over x is 1, x over x is 1, x over x is 1. So this thing simplifies to 1. So now when I use my shortcut right here, where I want to subtract my exponents, my top exponent from my bottom exponent, I'll have x to the 4 minus 4, or x to the 0. 0. And so when we simplify it this way, we know that the answer is 1. So x to the 0 equals 1. So anytime that you have 0 in your exponent, as long as the base of your exponent is not 0, then your answer is going to be 1. Because when you expand it out, all of your numbers or variables will simplify to be 1, so your entire fraction will be 1. So anything to the 0 power is equal to 1. So you can write that in a generic form. For our shortcut, we can say x to the m over x to the m equals x to the m minus m, which equals x to the 0, which equals 1.